everybody, today we're going to talk about intermolecular forces, affectionately known as IMFs. Okay? Alright, so let's get started with this. So what does IMFs stand for? What does that mean? Intermolecular forces, let's break that down. So we got Yoda up here in the corner because it's a little bit of Yoda talk. Okay, so inter means between, molecular means molecules, and then forces are like attractions. So really what we're talking about here are the attractions that are happening between molecules. Okay, and we'll go into that in a little bit more detail here in a minute. All right, so I've got a chart here that might be helpful for you to write down. This is going to kind of summarize everything, put it all together for you. And on the left side, you have the overall strength. We're going to go from the weakest down to the strongest. Okay, we'll talk about the type of attraction and the overall idea. Now, overall, the idea, the first ones or the weakest ones are actually the intermolecular forces. Those are the ones that are between the molecules. To give you a better idea of what that is, I've got a couple models here. So we built these models, in the past. So with these intermolecular forces, really what we're talking about is the attraction that's happening not within the molecule itself. We're talking about the actual attraction. What's keeping these molecules together? Okay, or what's having them have an attraction together? That is what an intermolecular force or intermolecular attraction is. All right, so here are the different kinds that we're going to be talking about today. London dispersion forces, those are the weakest. Now we're going to go in more in depth with all of these, so just save some room in your notes for this, but again, this is a nice overview chart. The next strongest are the dipole-dipole attractions, and then after that are the hydrogen bonding. Okay, so that's the strongest. Hydrogen bonding is the strongest of the intermolecular forces. Okay. Now, if we continue on beyond that, we have the intramolecular forces. Now, what that's talking about, as we go back to our model again, that's now talking about the bonds between the atoms within the molecule, and that's what we've have been talking about in the last semester and continue on this semester as well. So this attraction, or this bond inside of this molecule, these are always going to be stronger than any attraction between two molecules. Okay, so the intramolecular force, and this bond is going to be stronger than any intermolecular attraction between the two molecules. Okay, so let's go through these. These are the ones that we've covered and talked about already. So covalent single bonds, double bonds, and then that covalent triple bond is the strongest of the intramolecular forces. Okay, but for this, these notes, we're going to really focus in on these IMFs, the intermolecular forces, going here. Okay, so let's look at hydrogen bonding first. So we're going to start at the strongest. Okay, so why is hydrogen bonding so darn strong? Now we represent it with 3 dots. Okay, that's how we represent it. And really what's going on here is we have this, if you have a very polar covalent bond within a molecule, so nitrogen and hydrogen, oxygen, hydrogen, fluorine. Like for example, fluorine has electronegativity 4, and then the hydrogen is 2.1. So that's a big difference. It's almost a difference of 2. So that means that these are very polar covalent. Okay, so that leads to these 3 are really the ones we're looking at for hydrogen bonding. Hydrogen with an F, an O, or an N, and it's because they are very polar covalent bonds. Okay, it creates a very strong partial positive and a partial negative charge that get attracted to one another, and that creates what we call the hydrogen bond. Okay, a way to remember that is we say hydrogen bonding is FON. It's FON, isn't it FON? F-O-N, just remember that. Hydrogen with an F, an O, or an N. Alright, so now let's look at the next one. The next one is dipole-dipole. Dipole-dipole is very similar to hydrogen bonding. Okay, so don't worry, it's pretty easy. Really what we're looking at is instead of being very polar covalent, it's just polar covalent. Okay, so this bond not quite as polar. Okay, so as a result, what we get here is, it's really any other polar covalent bond. It just creates a smaller partial positive and partial negative charge that attract the molecules. Okay, so that's what we call a dipole-dipole. Okay, let's go to the third one. Third one is the weakest. It's my personal favorite. It's just so cute. The London dispersion forces. And what we're dealing with here is we've got these nonpolar molecules, and overall they're neutral, but their electrons are constantly zipping around. Okay, so they're constantly, sometimes, and when they get to one side, they're going to create a temporary little attraction, and go to the other side, a temporary little repulsion, and for a tiny moment, okay, the electrons on one side of that molecule. Okay, so like here we have methane. Okay, so and it's nonpolar, right? It's symmetrical, but then for a tiny little second, it's got a few more electrons on this side than it does on the other side. So what that does is that changes the molecule from being totally spherical and no dipole and totally nonpolar, and it creates just a temporary small little partial charge. And we call those induced dipoles or temporary attractions. Okay, I've got a couple of animations here to kind of illustrate that. So what's going on here is exactly that process. You have a couple of nonpolar molecules, okay, but when they get kind of close by each other, you just have this real temporary dipole that's created. Okay, and the reason why is when they get close to one another, those electrons are zipping around, and for just an instant, there's a tiny attraction between the positive charge on this atom or molecule and the electrons, and then the electrons repel each other. Okay, so this just instantaneous tiny dipole is created. Okay, and so it's temporary dipole, and you can see up here. So you get this little negative on this side and a little positive here, and what that does is that temporary charge imbalance sets off a ripple of dipole-dipole attractions. Okay, so just for a tiny second, you can see what happens here is it's positive, and then as those electrons are zipping around, it creates this little attraction. Now it's really weak, but it's there, okay, and it's enough to keep that, get the molecules to stick together, okay, and get attracted to one another. All right, so let's kind of wrap this thing up here with some ideas, and look at the big picture. All right, so here now these are all, if you look at these that we've got up here, these are all nonpolar. Okay, so they're all organic molecules that are symmetrical and are nonpolar. So we've got with 2 carbons, 3 carbons, and 4 carbons. So how are these guys different, or is this guy going to be slightly have stronger attraction than this one, or how does that work? All right, well, let's look at this. As I go down here from 2 carbons to 3 to 4, our molecular mass and our atoms increase, right? So we're getting more mass and more atoms. As we add more atoms, these are all nonpolar, but I'm adding more atoms, and as I add more atoms, I'm also adding more electrons, okay? So the number of electrons increases. As I increase more electrons, that increases the attractive force between these molecules. So there's more electrons zipping around here, okay? Creating that those temporary dipoles, or those temporary attractions. And as a result, it makes it harder to get this guy to boil. It's harder for this guy to evaporate. This one is a little bit strong. It's going to be stronger than this one, and this one's going to be stronger than this one. Okay. The smaller the molecule is, the weaker that London dispersion attraction is going to be, just because there's fewer electrons. Okay, there's not as much going on there. All right, so we're going to have some summary, and then we'll do some questions. Okay, so here's a big summary. IMFs, hydrogen bonding, the strongest. Put a strong guy up here for you. Okay, and we denote that with 3 dots. Okay, so here's your hydrogen with the O. Remember, hydrogen bonding is Phan. Dipole-dipole attractions, we denote that with 2 dots, okay? And again, that's just like hydrogen bonding, except it's anything other than the hydrogen with the F, O, or N, okay? And then lastly, the weak guy here, the weakest of all of the IMFs, is the London dispersion forces. We denote that with 1 dot in between, and those are just those temporary dipoles in between there. All right, so here's a couple of questions for you. After one more little summary, what does this mean? Strong IMFs. They're hard to break apart. Okay, they have high boiling points. They are slow to evaporate. Okay, so if you have a weak IMF, on the other hand, it's easy to break apart. It boils at a low temperature, low boiling point, and it evaporates very quickly and very easily. All right, now that I've built up your excitement, you guys ready for some questions? Here we go. Look at this. Okay, hopefully you answered box 1. Okay, so if we're going from weakest to strongest, we have only 2 carbons here and 3 carbons here. So remember, these are both nonpolar, so these would be both London dispersion, but this guy has more carbons, he's bigger, so he'd be a little bit stronger. And then this one over here, look, we've got the H with the O, hydrogen bonding, so that one's going to be the strongest of them all. Okay, so that's why box 2 is incorrect. It has that hydrogen bonding first, so it goes weak, a little bit stronger, strongest. All right, here's another one for you. All right, hopefully you said propanol. Propanol. Which one's going to boil at which one's going to boil at the highest temperature means which one is hardest to break apart. Okay, and propanol, because it has, here's your hydrogen bonding, right? That's going to be the strongest. It's going to be the toughest to get this guy to go from a liquid to the gas. It's going to be hard to do that. Okay. All right. Here's another one for you. All right. Oops. All right. So for this one, okay, these both have the same number of atoms and about the same molecular weight. But here's the deal. This one is a solid at room temperature, and this one is a gas at room temperature. Why is that? Well, it is because this one is, you're going to have dipole-dipole attractions. Okay, so this one is nonpolar, right? So it's going to have London dispersion. So for this one, it takes less energy to get this guy to evaporate or break apart. Okay, because this one's weak. The bromine gas, just at 0 degrees Celsius, it'll turn into a gas. It doesn't take much energy. This one, because dipole-dipole is stronger, it's going to stay together as a solid. All right, if you guys have any questions, go back, rewatch the video, pause it, and be sure you ask your instructor if you have any questions.